The quantum advantage: quantum computers have the potential to solve certain problems much faster than classical computers. This is because quantum computers use quantum bits or qubits, which can exist in multiple states simultaneously, allowing for parallel processing of vast amounts of data. A function of the form f(x) equals 1/2 x x1 caret 2 plus 1/2 y y1 caret 2, where x1 y1 is each point on the sheet of paper. The function should be a quadratic function that goes through all the given points. This is known as a least squares optimization problem. The least squares optimization problem is a classic problem in machine learning and statistics, and it's known to be NP-hard. So, the question is, what are the best algorithms for solving this problem in practice? In classical optimization, the best algorithms for solving the least squares problem are the Gauss-Markov theorem, which is a well-known result in linear algebra. This theorem states that the best fit line is the one that minimizes the sum of the squared errors. The Gauss-Markov theorem can be used to find the best fit quadratic function as well. Another classical algorithm is the method of least squares using QR decomposition. The QR decomposition is a factorization of the matrix into a product of an orthogonal matrix and an upper triangular matrix. This can be used to solve the least squares problem efficiently. In contrast, quantum algorithms can solve the least squares problem much faster than classical algorithms. The researchers aim to develop a new method for decoding messages that are encoded with noise, which is a common issue in many applications. Understanding the problem of decoding noisy messages. The problem of decoding noisy messages is a fundamental challenge in computer science, with far-reaching implications in various fields such as error-correcting codes, cryptography, and data transmission. In many real-world applications, messages are transmitted over noisy channels, which can introduce errors into the received signal. These errors can be caused by various factors, including electromagnetic interference, thermal noise, or even intentional jamming. The goal of decoding noisy messages is to recover the original, accurate message from the noisy received signal. This problem is closely related to the concept of error-correcting codes, which are designed to detect and correct errors in digital data. In the context of cryptography, decoding noisy messages is essential for ensuring the security and integrity of encrypted data. Google's new quantum algorithms can outperform classical ones. They recognize everything as waves using a mathematical tool called a quantum Fourier transform. In doing so, they can manipulate the quantum system so that bigger waves correspond to better solutions. Understanding the problem in quantum systems, amplitudes represent the probability of different outcomes. However, with an exponentially large number of possible outcomes, it becomes challenging to identify the amplitudes that correspond to the best solutions. Theoretical background: the team's initial concern was that their quantum algorithm was too specialized, with limited potential for broader applications. However, by consulting with a coding theory expert, they were able to identify potential connections to existing classical algorithms. The expert searched for any known classical algorithms that might match the quantum speedup. She examined the properties of the quantum algorithm, looking for similarities with existing classical algorithms. "We have a lot of work to do, but we have made significant progress." Theoretical breakthrough: the discovery of DQI has sent shockwaves throughout the quantum community, with many experts hailing it as a major breakthrough. The concept of DQI is based on the idea that a quantum computer can be used to solve complex problems that are currently unsolvable by classical computers. Theoretical models have shown that DQI can be used to solve problems that are exponentially more complex than those that can be solved by classical computers. The concept of DQI is based on the idea that a quantum computer can be used to manipulate the quantum states of particles in a way that is not possible with classical computers.